Oceans are vast, continuous bodies of salt water that cover the majority of Earth's surface and form the foundation of the planet's life support system. They are not merely large collections of water, but dynamic, interconnected systems that influence climate, chemistry, biology, and geology on a global scale. More than 70% of Earth is covered by ocean water, making oceans the defining feature of the planet when viewed from space. This immense coverage means that nearly every natural process on Earth is shaped, directly or indirectly, by the oceans. One of the most fundamental roles of oceans is their ability to regulate Earth's climate. Water has a high heat capacity, allowing oceans to absorb vast amounts of solar energy without rapidly changing temperature. During warm periods, oceans store heat. During cooler periods, they release it back into the atmosphere. This moderating effect prevents extreme temperature swings and makes Earth habitable for complex life. Without oceans acting as a thermal buffer, large portions of the planet would experience far harsher and more unstable climates. Oceans also play a critical role in the movement of heat around the globe. Warm water from equatorial regions and cooler water from polar regions are constantly redistributed through large-scale circulation patterns. These movements influence wind systems, rainfall distribution, seasonal weather, and long-term climate patterns. Many regions owe their relatively warm climates not to their latitude, but to nearby oceanic influence. Another essential function of oceans is their contribution to the planet's oxygen supply. Microscopic marine organisms, especially photosynthetic plankton, use sunlight, carbon dioxide, and nutrients to produce energy, releasing oxygen as a byproduct. A significant portion of the oxygen in Earth's atmosphere originates from these ocean-based processes. Unlike forests, which are highly visible and widely recognized, this oxygen production happens largely out of sight, making the oceans an often overlooked contributor to breathable air. Oceans are also central to Earth's carbon cycle. They absorb large quantities of carbon dioxide from the atmosphere, helping to regulate greenhouse gas levels. Some of this carbon remains dissolved in seawater, while some is incorporated into living organisms or sinks to the seafloor in the form of organic matter and sediments. Over geological timescales, this process has helped stabilize Earth's climate. However, changes in carbon absorption can significantly affect ocean chemistry, with wide-ranging consequences for marine life and global climate systems. From a biological perspective, oceans are home to an extraordinary diversity of life. They contain ecosystems ranging from sunlit surface waters filled with microscopic organisms to deep, dark environments where life survives under immense pressure and near-freezing temperatures. Marine organisms have evolved unique adaptations to survive in conditions that would be lethal on land, such as extreme pressure, limited light, and low temperatures. stretches from the western coasts of the Americas to Asia and Australia. The Pacific contains the deepest known point on the planet, the Mariana Trench, and is characterized by vast open water regions, powerful currents, and intense geological activity. Many of Earth's most active volcanoes and earthquake zones surround this ocean, forming what is known as the Ring of Fire. Its immense size allows it to store enormous amounts of heat, making it a dominant force in regulating global climate patterns. The Atlantic Ocean is the second largest ocean and plays a central role in human history. It separates the Americas from Europe and Africa and has long served as a major corridor for exploration, migration, trade, and cultural exchange. Compared to the Pacific, the Atlantic is narrow, but features some of the world's most productive fishing grounds and busiest shipping routes. A prominent feature of this ocean is the Mid-Atlantic Ridge, an underwater mountain chain where new oceanic crust is constantly being formed as tectonic plates slowly move apart. The Indian Ocean is the third largest and is unique in several important ways. It is bordered by Africa, Asia, Australia, and the Southern Ocean, and it is the warmest of the world's oceans overall. Seasonal wind patterns known as monsoons strongly influence its circulation, causing dramatic shifts in currents and weather throughout the year. These monsoon systems have shaped agriculture, trade, and settlement patterns across surrounding regions for thousands of years. The Indian Ocean also contains extensive coral reefs, deep ocean basins, and some of the world's most important maritime choke points. Encircling the southernmost part of the planet is the Southern Ocean, a relatively recent addition to the list of recognized oceans. It surrounds Antarctica and is defined more by its currents than by continental boundaries. The Antarctic circumpolar current flows uninterrupted around the continent, linking the Atlantic, Pacific, and Indian Oceans, and playing a vital role in global heat and nutrient exchange. The Southern Ocean is known for its cold temperatures, strong winds, and seasonal sea ice. Despite these harsh conditions, it supports rich ecosystems, including large populations of krill that form the base of the Antarctic food web. The smallest and shallowest of the five is the Arctic Ocean, located around the North Pole. Much of this ocean is covered by sea ice for large parts of the year, though the extent of that ice varies seasonally. The Arctic Ocean receives fresh water from many large rivers, which affects its salinity and circulation. Its ecosystems are specially adapted to cold, low-light conditions, supporting species such as polar bears, seals, and cold-water fish. Changes in this ocean are closely monitored because it is warming faster than any other ocean, making it a key indicator of global climate change. Although these five oceans are described separately, they are not isolated systems. Water masses move freely between them, driven by currents, winds, and differences in temperature and salinity. Events in one ocean can influence conditions in another, sometimes thousands of kilometers away. For example, temperature changes in the Pacific can alter weather patterns across the Atlantic and Indian Oceans through complex atmospheric connections. The classification into five oceans reflects humanity's attempt to understand and organize a planet-spanning system that is continuous by nature. Each ocean has distinct characteristics shaped by geography, climate, and geology, yet all are part of a single global ocean that sustains life on Earth. Recognizing both their individuality and their interdependence is essential for understanding how the ocean system works as a whole. The sheer size, depth, and volume of Earth's oceans are difficult to comprehend, yet these physical dimensions are central to how the planet functions. Oceans cover more than two-thirds of Earth's surface and contain nearly all of its free water. When measured as a single body, the global ocean forms the largest continuous environment on the planet, dwarfing all terrestrial collisions crush unprotected objects and would be instantly fatal to most land-based life forms. Yet despite this, specialized organisms thrive at such depths, demonstrating how life is adapted to even the most extreme environments on Earth. The volume of water contained in the oceans is equally staggering. Oceans hold about 1.3 billion cubic kilometers of water, accounting for roughly 97% of all water on the planet. The remaining fraction is locked away in glaciers, ice caps, groundwater, lakes, rivers, and the atmosphere. This immense volume allows oceans to dominate the global water cycle, driving evaporation, cloud formation, precipitation, and freshwater distribution across continents. Because of their volume, oceans also serve as massive reservoirs for dissolved substances. Salts, gases, nutrients, and carbon compounds circulate within this water mass, influencing chemistry on a planetary scale. Small changes in ocean temperature or circulation can shift these balances, leading to wide-ranging effects on climate and ecosystems. The depth and volume of oceans give them inertia, meaning changes occur slowly, but once underway, they can be long-lasting and difficult to reverse. The size of ocean basins is closely tied to Earth's geological structure. Beneath the oceans lie vast plates of dense oceanic crust, which sit lower than continental crust and allow water to pool in deep basins. Mid-ocean ridges stretch tens of thousands of kilometers across the seafloor, marking areas where tectonic plates pull apart and new crust forms. These underwater mountain chains are among the longest geological features on Earth, even though most remain hidden beneath kilometers of water. Despite centuries of exploration, much of the ocean's depth remains poorly mapped. While the surface of the Moon and Mars has been charted in greater detail than the deep sea floor, large areas of the oceans are known only through indirect measurements. The challenge lies in the vast distances, extreme pressures, and darkness that make deep ocean exploration technically demanding and expensive. As a result, new features and records continue to be discovered even in the modern era. The combination of immense surface area, extreme depth, and enormous volume makes the oceans uniquely influential within Earth's system. They store heat, move energy, cycle water and carbon, and provide space for the majority of life on the planet. Understanding the scale of the oceans is essential for grasping why changes within them, whether natural or human-driven, have consequences that extend far beyond the water itself, shaping the future of Earth as a whole. The ocean is not a uniform body of water, but a layered and organized system structured both horizontally across the planet and vertically from the surface to the deepest trenches. Scientists describe this structure using zones that reflect changes in light, temperature, pressure, and biological activity. These zones help explain why different forms of life exist where they do, and how energy and materials move through the ocean. Horizontally, the ocean is divided into regions based on distance from land and depth of the seafloor. Closest to the continents is the coastal ocean, which includes waters over the continental shelf. Although this region makes up a relatively small portion of the ocean's total area, it is among the most biologically productive. Sunlight reaches the seafloor in many coastal areas. Nutrients flow in from rivers and upwelling currents, and ecosystems such as kelp forests, seagrass meadows, and coral reefs thrive. Human activity is also most concentrated here, making coastal regions both economically valuable and environmentally vulnerable. Beyond the continental shelf lies the open ocean, sometimes called the pelagic ocean. This vast region extends across deep water far from land and represents the largest habitat on Earth. Unlike coastal ocean is divided into depth-based zones that reflect how conditions change with distance from the surface. The uppermost layer is the sunlit zone, where sunlight penetrates sufficiently for photosynthesis to occur. This zone contains the majority of ocean life and nearly all primary production. Phytoplankton, microscopic algae, use sunlight to convert carbon dioxide into organic matter, supporting food webs that extend from tiny zooplankton to the largest animals on Earth. Below the sunlit zone lies a region where light rapidly diminishes. Here, photosynthesis becomes impossible, and life must rely on organic material sinking from above or alternative energy sources. Temperatures drop, pressure increases, and organisms exhibit adaptations such as large eyes, slow metabolisms, and vertical migration behaviors. Many species move upward at night to feed near the surface and descend during the day to avoid predators, linking surface and deep ecosystems. Deeper still is the dark ocean, where no sunlight penetrates at all. This realm makes up the vast majority of the ocean's volume and remains one of the least understood environments on Earth. Temperatures are near freezing, pressure is extreme, and food is scarce. Despite these harsh conditions, life persists. Some organisms produce their own light through bioluminescence, using it to attract prey, deter predators, or communicate in the darkness. At the greatest depths are the deepest trenches and basins, where conditions reach their extremes. These zones are characterized by immense pressure, stable cold temperatures, and complete darkness. Life here is highly specialized, with organisms often exhibiting soft bodies, slow growth, and unique biochemical adaptations that allow their cells to function under crushing pressure. In some areas, life is supported not by sunlight but by chemical energy released from the Earth's interior, such as at hydrothermal vents. The structure of the ocean is not static. Boundaries between zones shift with seasons, latitude, and climate conditions. Warm tropical waters allow sunlight to penetrate deeper, while colder or more turbid waters limit light penetration. Storms, currents, and mixing events can temporarily disrupt layering, redistributing heat, oxygen, and nutrients between zones. Understanding the ocean's structure is essential because it determines how energy flows, where life can exist, and how the ocean interacts with the atmosphere. Climate change, pollution, and human activity can alter these layers by warming surface waters, reducing oxygen at depth, or changing circulation patterns. Such changes can ripple through the entire system, affecting ecosystems far removed from their point of origin. The ocean's layered structure reveals a world that is highly organized, yet deeply interconnected. From sunlit surface waters to the darkest depths, each zone plays a role in maintaining the balance of Earth's largest and most influential environment. Beneath the surface of the oceans lies a vast and complex landscape that rivals the diversity of Earth's continents. The ocean floor, also known as the seafloor, is not a flat plain but a dynamic terrain shaped by tectonic forces, volcanic activity, sediment deposition, and erosion over millions of years. Understanding the features of the ocean floor is essential for explaining how oceans form, how continents move, and how life thrives in the deep. Closest to land are the continental margins, which form the transition between continents and deep ocean basins. The first part of this margin is the continental shelf, a gently sloping, relatively shallow extension of the continent submerged beneath seawater. Continental shelves vary greatly in width, stretching hundreds of kilometers in some regions and narrowing sharply in others. These areas are among the most productive on Earth because sunlight can reach the seafloor, nutrients are abundant, and biological activity is intense. Many of the world's major fisheries are located on continental shelves. Beyond the continental shelf lies the continental slope, where the seafloor drops some regions, especially where tectonic activity is high, the continental rise may be absent, replaced instead by deep trenches that plunge abruptly into the Earth's crust. The deep ocean basin makes up the largest portion of the seafloor and contains some of its most distinctive features. Vast abyssal plains stretch across thousands of kilometers, forming some of the flattest areas on the planet. These plains are covered by fine sediments that settle slowly from the surface waters above, accumulating over millions of years. Despite their apparent emptiness, abyssal plains host specialized life adapted to cold, dark, and food-limited conditions. Rising from the deep basins are seamounts, underwater mountains formed by volcanic activity. Some seamounts grow tall enough to reach the ocean surface, becoming islands, while others remain entirely submerged. These structures disrupt ocean currents and create localized upwelling, bringing nutrients from deep water toward the surface. As a result, seamounts often support rich and diverse ecosystems, acting as biological hotspots in the open ocean. One of the most significant features of the ocean floor is the global system of mid-ocean ridges. These immense underwater mountain chains form where tectonic plates move apart and magma rises from the mantle to create new oceanic crust. A prominent example is the Mid-Atlantic Ridge, which runs down the center of the Atlantic Ocean. Mid-ocean ridges are sites of frequent volcanic activity and play a central role in shaping the size and structure of ocean basins over geological time. In contrast to ridges are deep-sea trenches, the deepest parts of the ocean floor. These narrow, elongated depressions form where one tectonic plate is forced beneath another in a process known as subduction. Trenches represent areas where old oceanic crust is recycled back into Earth's interior. They are associated with powerful earthquakes and volcanic arcs and host some of the most extreme environments on the planet. The ocean floor is far from static. New crust is continuously created at mid-ocean ridges, while old crust is destroyed at trenches, driving the slow but relentless movement of tectonic plates. This process influences the position of continents, the opening and closing of ocean basins, and the long-term evolution of Earth's surface. Despite its importance, much of the ocean floor remains poorly explored. Extreme depths, crushing pressure, and vast distances make direct observation difficult. Advances in sonar mapping, remotely operated vehicles, and deep-sea submersibles have revealed remarkable details, yet large areas are still mapped only in broad outlines. Each new exploration has the potential to uncover unknown geological features and previously unseen ecosystems. The ocean floor is a record of Earth's internal processes and surface history, written in rock and sediment. From shallow continental shelves to the deepest trenches, it shapes ocean circulation, supports life, and drives the slow transformation of the planet itself. Seawater is far more than plain water with salt mixed in. It is a complex chemical solution shaped by geological processes, biological activity, and constant interaction with the atmosphere. The chemistry of ocean water influences climate, marine life, and even the composition of Earth's air. Understanding what seawater contains and how it behaves chemically is essential for explaining how oceans function as a global system. One of the most defining features of ocean water is its salinity. Salinity refers to the concentration of dissolved salts in water, usually expressed in parts per thousand. On average, seawater has a salinity of about 35 parts per thousand, meaning that for every kilogram of seawater, roughly 35 grams are dissolved salts. The most abundant of these salts is sodium chloride, the same compound found in table salt, but seawater also contains magnesium, sulfate, calcium, potassium, and many other dissolved ions. The saltiness of substances directly into ocean water. While fresh water continuously enters the oceans through rainfall and rivers, salts tend to remain behind when water evaporates, gradually increasing salinity over geological time. Today, salinity levels are relatively stable because inputs and removals are balanced. Salinity is not uniform across the oceans. Regions with high evaporation and little rainfall, such as subtropical areas, tend to have higher salinity. In contrast, areas near river mouths, heavy rainfall or melting ice often have lower salinity. These differences may seem small, but they play a major role in ocean circulation, as water density is influenced by both temperature and salinity. Denser water sinks, while less dense water rises, helping drive large-scale movement of ocean water around the planet. Another critical aspect of ocean chemistry is the presence of dissolved gases. Oxygen, carbon dioxide, and nitrogen constantly move between the ocean and the atmosphere. Oxygen enters surface waters through direct exchange with air and through photosynthesis by marine plants and plankton. This oxygen is essential for marine animals, particularly in surface and mid-depth waters. In deeper regions, where circulation is slow and organic matter decomposes, oxygen levels can be very low, creating challenging conditions for life. Carbon dioxide plays a particularly important role in ocean chemistry. When carbon dioxide dissolves in seawater, it reacts with water to form carbonic acid, which then breaks down into bicarbonate and carbonate ions. These chemical forms allow the ocean to store vast amounts of carbon, making it a major regulator of atmospheric carbon dioxide levels. However, increases in carbon dioxide absorption lead to changes in ocean acidity, a process known as ocean acidification. Even small shifts in acidity can affect organisms that build shells or skeletons from calcium carbonate. The pH of seawater is slightly basic, typically around 8.1, meaning it is not acidic. This stable pH is maintained by natural buffering systems involving carbonate and bicarbonate ions. These buffers help resist rapid changes in acidity, but they have limits. As more carbon dioxide enters the oceans due to human activities, these buffering systems are being pushed beyond their natural range, leading to gradual but significant chemical changes. Seawater also contains a wide range of nutrients essential for life, including nitrogen, phosphorus, silicon, and iron. These nutrients support the growth of phytoplankton, which form the base of marine food webs. Nutrient concentrations vary widely depending on location and depth. Surface waters in many open ocean regions are nutrient poor because nutrients are rapidly consumed by organisms, while deeper waters tend to be nutrient-rich due to the breakdown of sinking organic material. The chemistry of ocean water is closely linked to biological activity. Marine organisms constantly modify their chemical environment by taking up nutrients, releasing waste products, and building shells or skeletons. In turn, chemical conditions influence where different species can survive and thrive. This continuous interaction between chemistry and biology helps maintain the balance of ocean ecosystems. Overall, ocean water chemistry reflects the combined influence of Earth's rocks, atmosphere, and living systems. Salts, gases, nutrients, and buffering compounds work together to create an environment capable of supporting an immense diversity of life. Changes to this delicate chemical balance, whether natural or human-driven, can have far-reaching consequences for oceans and the planet as a whole. Ocean currents are the vast, continuous movements of seawater that circulate through the world's oceans, redistributing heat, nutrients, gases, and organisms across the planet. These currents are not random. They follow consistent patterns shaped by wind, Earth's rotation, differences in water density, and the Together, surface and deep ocean currents form a global circulation system that plays a decisive role in climate, weather, and marine life. At the ocean's surface, currents are primarily driven by wind. Persistent global wind patterns push surface waters, creating large-scale flows that can travel thousands of kilometers. As winds move water, Earth's rotation causes these currents to curve, a result of the Coriolis effect. In the northern hemisphere, currents tend to curve to the right, while in the southern hemisphere they curve to the left. This deflection leads to the formation of massive circular systems known as gyres, which dominate the surface circulation of each major ocean basin. Surface currents are especially important for moving heat around the planet. Warm water from tropical regions flows toward higher latitudes, while cooler water moves back toward the equator. This exchange moderates regional climates and explains why some coastal areas experience milder temperatures than inland regions at similar latitudes. Without this constant movement of heat by ocean currents, global temperature differences would be far more extreme, and many regions would be far less hospitable to life. Beneath the surface lies a very different but equally important system of circulation, known as deep ocean or thermohaline circulation. This system is driven by differences in water density, which depend on temperature and salinity. Cold, salty water is denser than warm or fresher water, so it sinks. In certain high-latitude regions, surface water cools, becomes saltier due to ice formation, and sinks to great depths. This sinking water then flows slowly through the deep ocean, eventually rising elsewhere in a process that can take centuries to complete. Thermohaline circulation connects all of the world's oceans into a single, global conveyor-like system. Although these deep currents move far more slowly than surface currents, they transport enormous volumes of water and play a crucial role in long-term climate regulation. By storing and redistributing heat and carbon over long timescales, deep ocean circulation helps stabilize Earth's climate and influences atmospheric carbon dioxide levels. Currents also have a profound impact on marine ecosystems. Where surface currents move water away from a coastline or diverge in the open ocean, deeper water often rises to replace it in a process called upwelling. This rising water is typically rich in nutrients that have accumulated at depth from the decomposition of organic matter. Upwelling zones are among the most biologically productive areas in the ocean, supporting large populations of plankton, fish, seabirds, and marine mammals. In contrast, regions where surface water converges and sinks tend to be nutrient poor at the surface. These areas often appear clear and blue because there is less plankton in the water. Despite lower productivity, such regions still play important roles in global circulation and gas exchange between the ocean and atmosphere. Ocean currents also influence weather patterns on land. By affecting sea surface temperatures, they help shape atmospheric pressure systems, rainfall distribution, and storm tracks. Changes in current strength or direction can alter regional climates, sometimes leading to droughts, floods, or shifts in seasonal weather. Because of this close connection, monitoring ocean circulation is essential for understanding and predicting climate variability. Currents are not fixed. They vary over time in response to seasonal changes, atmospheric conditions, and longer-term climate cycles. Natural climate patterns can strengthen or weaken currents, alter their paths, or change how heat and nutrients are distributed. Human-driven climate change adds another layer of complexity, as warming temperatures and melting ice can modify salinity and density patterns, potentially disrupting established circulation systems. The study of ocean currents reveals the oceans as a constantly moving, interconnected system, rather than a static body of water. These currents link distant parts of the planet, allowing changes in one region to influence conditions life through the oceans. Currents help maintain the delicate balance that makes Earth a living planet. The surface of the ocean is rarely still. It is constantly shaped by tides, waves, and, in rare cases, tsunamis, each driven by different forces and operating on very different scales of time and energy. Together, these movements influence coastlines, marine ecosystems, navigation, and human settlements, making them some of the most visible and powerful expressions of ocean dynamics. Tides are the slow, regular rise and fall of sea level that occur along coastlines and across the open ocean. They are primarily caused by the gravitational pull exerted on Earth's water by the Moon, with a smaller contribution from the Sun. As Earth rotates, this gravitational interaction creates bulges of water on opposite sides of the planet. When a coastal area rotates into one of these bulges, sea level rises, producing high tide. As it rotates away, sea level falls, producing low tide. Most coastlines experience 2 high tides and 2 low tides each day, though the exact timing and height vary by location. This pattern occurs because Earth rotates beneath the tidal bulges, rather than the bulges moving around Earth. The shape of coastlines, the depth of nearby waters, and the presence of bays or estuaries can amplify or reduce tidal ranges. In some locations, tides rise and fall only a small amount, while in others the difference between high and low tide can reach several meters. The alignment of the Sun, Moon, and Earth influences tidal strength. When the Sun and Moon line up, their gravitational forces combine, producing higher than normal high tides and lower than normal low tides, known as spring tides. When the Sun and Moon are at right angles relative to Earth, their gravitational effects partially cancel out, resulting in weaker tides called neap tides. These cycles affect coastal flooding, sediment transport, and the exposure of intertidal ecosystems. Waves, unlike tides, are primarily generated by wind. As wind blows across the surface of the ocean, it transfers energy to the water, creating ripples that grow into waves. The size of a wave depends on wind speed, wind duration, and the distance over which the wind blows, known as fetch. Stronger winds blowing over longer distances produce larger waves with more energy. Most ocean waves involve the movement of energy rather than the movement of water itself. Individual water particles move in circular or elliptical paths, returning nearly to their original position as a wave passes. This means that waves can travel great distances across the ocean without transporting large amounts of water. Swells generated by distant storms can reach coastlines thousands of kilometers away, long after the winds that created them have disappeared. As waves approach shallow coastal waters, their behavior changes. The lower part of the wave begins to drag along the seafloor, slowing it down while the upper part continues moving forward. This causes the wave to grow taller and eventually break. Breaking waves release energy that shapes coastlines through erosion and sediment transport, constantly reshaping beaches, cliffs, and nearshore environments. Tsunamis are fundamentally different from wind-driven waves. They are generated by sudden disturbances of the seafloor, most commonly earthquakes, but also volcanic eruptions or underwater landslides. When a large volume of water is displaced, energy spreads outward across the ocean in all directions. In the open ocean, tsunami waves may be only a meter high or less, with wavelengths stretching hundreds of kilometers, making them difficult to detect. As a tsunami enters shallow coastal waters, its speed decreases, but its height increases dramatically. This transformation can produce towering waves or rapidly rising surges of water that inundate coastal areas with devastating force. Unlike typical waves that break near the shore, tsunamis can push far inland, carrying debris and causing widespread destruction. Tides, waves, and tsunamis interact with marine ecosystems ecosystems in complex ways. Tidal cycles expose and submerge coastal habitats, shaping the lives of organisms adapted to changing conditions. Waves mix surface waters, influence gas exchange with the atmosphere, and transport nutrients. Tsunamis, though rare, can radically alter coastal ecosystems in a matter of minutes, reshaping landscapes that took centuries to form. Together, these ocean movements reveal the dynamic nature of the sea. Driven by gravity, wind, and geological forces, tides, waves, and tsunamis demonstrate how energy moves through the ocean system and how closely ocean processes are linked to Earth's atmosphere, interior, and even its position in space. Light, temperature, and pressure change dramatically as depth increases in the ocean, creating some of the most extreme and varied environmental conditions found anywhere on Earth. These physical factors shape where life can exist, how organisms are adapted, and how energy moves through marine ecosystems. Understanding these gradients reveals why the ocean is structured into distinct layers and why the deep sea remains such a challenging environment. Sunlight is the primary source of energy for life in the upper ocean, but water absorbs and scatters light rapidly. Only the upper portion of the ocean receives enough light to support photosynthesis. This sunlit layer extends downward until light becomes too weak for plants and algae to produce energy. Below this depth, sunlight fades quickly, and eventually darkness becomes complete. The color of light also changes with depth, as longer wavelengths such as red are absorbed first, leaving blue light to penetrate the deepest. Because sunlight drives photosynthesis, its limited penetration has profound biological consequences. Nearly all primary production in the ocean occurs near the surface, where microscopic plants convert light energy into organic matter. This organic material then supports food webs that extend into darker depths as sinking particles, or as prey carried downward by migrating organisms. Without sunlight, deep ocean ecosystems depend entirely on energy originating from the surface or from chemical sources. Temperature in the ocean is closely tied to sunlight and depth. Surface waters are warmed by the sun, particularly in tropical regions, while deeper waters remain cold and stable. In many parts of the ocean, there is a zone where temperature drops rapidly with depth, forming a sharp boundary between warm surface water and colder deep water. Below this transition, temperatures change very little, often remaining just a few degrees above freezing regardless of location. This temperature structure plays a key role in ocean circulation. Warm water is less dense than cold water, so it tends to remain near the surface. Cold, dense water sinks and spreads through the deep ocean. These density differences help keep surface and deep waters separated, limiting mixing and influencing how heat, oxygen, and nutrients are distributed. Seasonal changes, storms, and currents can disrupt this layering, allowing heat and gases to move between layers. Pressure increases with depth at a steady and predictable rate. For every 10 meters of depth, pressure increases by roughly 1 atmosphere, equivalent to the air pressure at Earth's surface. At depths of thousands of meters, pressure becomes immense, exerting forces strong enough to crush most human-made objects. This extreme pressure shapes every aspect of deep-sea life, from the structure of cells to the chemistry of biological reactions. Marine organisms have evolved remarkable adaptations to cope with high pressure. Many deep-sea animals lack rigid structures like air-filled spaces or hard shells that would collapse under pressure. Instead, they often have soft bodies, flexible tissues, and specialized proteins that function under intense compression. These adaptations allow life to persist in conditions that would be lethal to surface-dwelling organisms. The combined effects of light, temperature, and pressure create distinct vertical habitats within the ocean. Surface waters are warm, well-lit, and relatively low pressure, supporting high biodiversity and productivity. Mid-depth regions experience fading light, cooler temperatures, and increasing pressure, favoring organisms adapted to low energy availability and wide-ranging movements. The deepest regions are cold, dark, and high-pressure environments where life is sparse, slow-growing, and highly specialized. These physical gradients also influence chemical processes in the ocean. Temperature affects how gases dissolve in water, with colder water holding more oxygen and carbon dioxide. Pressure influences the behavior of dissolved substances and the stability of certain compounds. Light controls chemical reactions driven by photosynthesis and affects how heat and energy enter the ocean system. Changes in light, temperature, and pressure patterns can have far-reaching consequences. Warming surface waters can strengthen layering, reducing the mixing that delivers oxygen to deeper waters and nutrients to the surface. Such changes can alter ecosystems, fisheries, and global climate feedbacks. Because of this, scientists closely monitor these physical factors to understand both natural variability and human-driven change. The vertical gradients of light, temperature, and pressure reveal the ocean as a world of extremes and transitions. From sunlit, life-rich surface waters to the cold, dark depths. These factors define the structure of marine environments and shape the remarkable adaptations that allow life to exist throughout the ocean's vast interior. Polar ocean represents some of the most extreme and influential marine environments on Earth. Found at the highest latitudes, these oceans are defined by cold temperatures, seasonal darkness or continuous daylight, and the presence of sea ice. Despite appearing barren and inhospitable, polar oceans play a critical role in regulating Earth's climate and support ecosystems, uniquely adapted to life at the edge of habitability. One of the most distinctive features of polar oceans is sea ice. Unlike icebergs, which form from glaciers on land, sea ice develops directly from freezing seawater. As seawater freezes, salt is expelled, making the surrounding water saltier and denser. This process contributes to the sinking of cold, dense water that helps drive deep ocean circulation. Sea ice expands and contracts with the seasons, reaching its greatest extent during winter and retreating during summer. Sea ice is not an empty, lifeless surface. Within and beneath it exists a complex habitat. Microscopic algae grow on the underside of the ice, using limited sunlight to carry out photosynthesis. These algae form the foundation of polar marine food webs, supporting small crustaceans, fish, birds, and mammals. When sea ice melts seasonally, it releases nutrients into the surrounding water, triggering bursts of biological productivity. Temperature in polar oceans is consistently low, often near the freezing point of seawater. Many organisms living in these waters have evolved antifreeze proteins in their blood and tissues that prevent ice crystals from forming inside their bodies. Metabolic processes are adapted to function efficiently in cold conditions, and growth rates are often slow. These adaptations allow life to persist in environments that would quickly kill organisms from warmer regions. Light availability in polar regions varies dramatically throughout the year. During summer, the sun may remain above the horizon for months, creating continuous daylight that fuels intense biological activity. In winter, long periods of darkness limit photosynthesis and reduce food availability. Marine organisms have adapted to this extreme seasonality through behaviors such as migration, energy storage, and flexible feeding strategies. Polar oceans are closely linked to global climate systems. Cold waters absorb large amounts of carbon dioxide from the atmosphere, making these regions important carbon sinks. The formation and melting of sea ice influence Earth's reflectivity, or albedo. Ice-covered surfaces reflect more sunlight back into space, helping to keep the planet cool. When ice melts, darker ocean water absorbs more heat, reinforcing warming trends. Ocean circulation is strongly influenced by polar processes. The sinking of cold, dense water in polar regions helps power deep ocean currents that transport heat, oxygen, and nutrients around the globe. Changes in temperature or freshwater input from melting ice can disrupt this circulation, with potential consequences for climate patterns far beyond the polar regions. Polar marine ecosystems include some of the most iconic animals on Earth. Large mammals, such as seals and whales, depend on polar waters for feeding and breeding. Many of these animals rely on thick layers of fat for insulation and energy storage. Fish and invertebrates form dense seasonal populations, taking advantage of short but intense periods of productivity. Despite their remoteness, polar oceans are increasingly affected by human activity. Rising global temperatures have led to reductions in sea ice extent and thickness, altering habitats and food webs. Increased accessibility has brought more shipping, fishing, and resource exploration to polar regions, raising concerns about pollution and ecosystem disturbance. Because polar ecosystems are finely balanced and slow to recover, even small disruptions can have long-lasting effects. Polar oceans act as early indicators of global environmental change. Shifts in ice cover, temperature, and species distribution are often observed here before appearing elsewhere. Studying these regions provides critical insight into how the ocean responds to climate change and how those responses may affect the rest of the planet. In their cold, ice-covered waters, polar oceans exert an influence far greater than their geographic size might suggest. They regulate climate, drive ocean circulation, and sustain specialized ecosystems adapted to extremes. Understanding polar oceans is essential for understanding the future of Earth's climate and the stability of the global ocean system. This ocean's ability to absorb, store, transfer, and redistribute carbon, atmospheric carbon dioxide levels would be far higher than they are today, and Earth's climate would be dramatically less stable. The exchange of carbon between the ocean, atmosphere, and biosphere is continuous, complex, and central to regulating global temperatures. Carbon enters the oceans primarily through direct exchange with the atmosphere. Carbon dioxide dissolves into surface waters, where it reacts with seawater to form a mixture of dissolved carbon species, including carbonic acid, bicarbonate, and carbonate ions. This chemical buffer allows the ocean to absorb large quantities of carbon without an immediate, proportional rise in partial pressure. Roughly a quarter to a third of all carbon dioxide released by human activities each year is taken up by the oceans, significantly slowing the rate of atmospheric warming. Once dissolved, carbon is moved and transformed through several interconnected processes, often referred to as the oceanic carbon pumps. The most immediate is the solubility pump, which depends on temperature. Cold water can hold more dissolved carbon dioxide than warm water. In high-latitude regions, surface waters cool, absorb carbon from the atmosphere, and then sink into the deep ocean, carrying that carbon with them. Over decades to centuries, these deep waters transport carbon throughout the global ocean interior, effectively removing it from short-term interaction with the atmosphere. A second major mechanism is the biological pump, driven by marine life. Phytoplankton at the ocean surface use carbon dioxide during photosynthesis, converting inorganic carbon into organic matter. These microscopic organisms form the base of marine food webs. When phytoplankton are consumed, die, or produce waste, some of the carbon contained in their bodies sinks as particles into deeper waters. A fraction of this material reaches the deep ocean and seafloor, where it can remain isolated from the atmosphere for hundreds to thousands of years. Over even longer timescales, the carbonate pump plays a role. Many marine organisms, such as corals and certain plankton, build shells and skeletons from calcium carbonate. When these organisms die, their shells can sink and accumulate as sediments. Over millions of years, these sediments become limestone and other carbonate rocks, locking carbon into Earth's crust. This geological pathway is one of the slowest but most enduring forms of carbon storage on the planet. Ocean circulation links these pumps into a global system. Regions such as the Southern Ocean are especially important because they connect surface waters with the deep ocean. Here, strong winds and upwelling bring carbon-rich deep waters back to the surface, where some carbon can be released to the atmosphere, while newly cooled waters absorb fresh carbon and sink again. This continuous overturning makes the Southern Ocean a critical control point in the global carbon cycle. While the ocean's role as a carbon sink helps moderate climate change, it also has consequences. As more carbon dioxide dissolves into seawater, chemical reactions shift ocean pH downward, a process known as ocean acidification. This reduces the availability of carbonate ions needed by shell-forming organisms, making it harder for corals, mollusks, and some plankton to build and maintain their structures. Although acidification does not directly drive climate, it alters marine ecosystems in ways that can feed back into carbon cycling by changing biological productivity and species composition. Human activity has begun to alter the balance of the ocean carbon cycle. Fossil fuel combustion, deforestation, and cement production release carbon far faster than natural geological processes can remove it. While oceans absorb a significant portion of this excess, their capacity is not unlimited. Warming surface waters reduce carbon solubility, potentially weakening the ocean's ability to take up additional carbon in the future. Changes in circulation patterns could further earliest phase of ocean exploration was driven by practical needs rather than science. Coastal peoples learned to read tides, winds, and currents through observation and experience. Ancient Polynesian navigators crossed immense distances across the open Pacific using stars, wave patterns, cloud formations, and the behavior of birds as guides. Similarly, Mediterranean civilizations developed ships and navigation techniques that enabled trade networks linking Africa, Europe, and Asia. These early mariners explored the ocean surface, but the depths below remained entirely beyond reach. During the age of exploration, beginning in the 15th century, ocean travel expanded dramatically. European expeditions crossed entire ocean basins, connecting previously isolated continents. These voyages produced the first global maps of coastlines and sea routes, transforming the oceans into corridors of commerce and empire. However, knowledge gained during this period was largely geographical rather than scientific. The ocean was measured in terms of distance and danger, not physical processes or biological complexity. Scientific ocean exploration began in earnest in the 19th century. Advances in navigation, shipbuilding, and measurement instruments allowed researchers to move beyond surface observations. One of the most influential milestones was the Challenger expedition of the 1870s, which systematically sampled ocean depths, temperatures, chemistry, and marine life. This voyage revealed that the deep ocean was not lifeless, as many had assumed, but inhabited by diverse organisms adapted to extreme pressure and darkness. It also marked the birth of modern oceanography as a scientific discipline. The 20th century brought rapid acceleration in ocean exploration, driven by technological innovation and geopolitical interests. Echo sounding and sonar allowed scientists to map the seafloor indirectly, revealing vast mountain ranges, trenches, and plains hidden beneath the waves. These discoveries revolutionized understanding of Earth's geology, providing critical evidence for plate tectonics. The ocean floor was no longer an imagined void, but a dynamic landscape shaped by volcanic activity and crustal movement. Direct exploration of the deep ocean became possible with the development of submersibles. Manned vehicles such as bathyscaphs allowed humans to descend thousands of meters below the surface, observing deep-sea environments firsthand. These missions confirmed the existence of life at extreme depths and pressures, including ecosystems supported not by sunlight, but by chemical energy from hydrothermal vents. Such discoveries fundamentally changed biological science, expanding the known limits of life on Earth. In parallel, remotely operated vehicles and autonomous underwater vehicles transformed ocean exploration. These robotic systems can remain underwater for extended periods, reach depths inaccessible to humans, and collect high-resolution imagery and samples. They have been essential for exploring the deepest trenches, mapping fragile ecosystems, and studying environments too dangerous or remote for crewed missions. Much of what is known today about deep ocean biodiversity comes from these technologies. Ocean exploration has also been closely linked to military and economic interests. During the Cold War, extensive seafloor mapping and acoustic research were driven by submarine navigation and detection. These efforts produced vast data sets that later benefited civilian science. Similarly, the search for undersea resources, cables, and energy reserves has expanded detailed knowledge of continental shelves and slopes, even as much of the open deep ocean remains poorly mapped. Despite centuries of effort, human exploration of a result, much of what is known about the ocean's shape and structure has been inferred indirectly through sound, gravity, and satellite measurements. Even today, despite advanced technology, the majority of the ocean floor remains far less well mapped than the surfaces of the Moon or Mars. The earliest attempts to map the ocean relied on simple depth measurements. Sailors lowered weighted lines over the side of ships to determine water depth near coasts and harbors. These soundings were essential for safe navigation, but provided only isolated data points. Vast regions of the open ocean remained unmapped, and the deep sea was assumed by many to be relatively flat and featureless. This misconception persisted well into the 19th century. The development of sonar in the early 20th century revolutionized ocean mapping. By emitting sound pulses and measuring the time it takes for echoes to return from the seafloor, scientists could estimate depth far more efficiently than with weighted lines. Ship-based echo sounding revealed dramatic undersea landscapes, including mountain chains, deep trenches, and expansive plains. These discoveries transformed understanding of Earth's geology and provided crucial evidence supporting theories of seafloor spreading and plate tectonics. As sonar technology advanced, multi-beam echo sounders replaced single-beam systems. Multi-beam sonar emits a fan of sound waves that can map wide swaths of the seafloor in a single pass, producing detailed three-dimensional representations of underwater terrain. These systems dramatically increased mapping resolution and efficiency, especially on continental shelves and slopes. However, they still require ships to physically pass over areas of interest, making global coverage slow and costly. Satellite technology added a new dimension to ocean mapping. Although satellites cannot directly see the seafloor through water, they can detect subtle variations in sea surface height caused by differences in gravitational pull from underwater features. Seamounts and ridges exert slightly stronger gravity, creating tiny bulges on the ocean surface that satellites can measure with remarkable precision. By analyzing these variations, scientists have produced global maps of seafloor topography at moderate resolution, revealing large-scale structures across entire ocean basins. Despite these advances, satellite-derived maps lack the fine detail needed for many scientific and practical purposes. High-resolution mapping still depends on ship-based sonar and underwater vehicles. Remotely operated vehicles and autonomous underwater vehicles can map complex terrain such as trenches, canyons, and coral reefs at close range, capturing fine-scale features and textures. These platforms are particularly valuable for studying fragile or hazardous environments that ships cannot approach closely. Large-scale mapping initiatives aim to close the gaps in global seafloor knowledge. International efforts seek to compile existing data and expand coverage through coordinated surveys. These projects highlight both the scale of the challenge and the uneven distribution of knowledge. Coastal regions and economically important areas are relatively well mapped, while vast expanses of the deep ocean remain sparsely surveyed or completely unexplored. Mapping the ocean is not only a scientific pursuit, but also a practical necessity. Accurate seafloor maps are essential for navigation, undersea cable and pipeline placement, resource management, hazard assessment, and environmental protection. Understanding seafloor shape helps scientists model ocean circulation, tsunami propagation, and habitat distribution. In this way, mapping underpins nearly every aspect of ocean science and marine policy. The difficulty of mapping is compounded by the sheer size of the ocean and the harsh conditions of the deep sea. Extreme pressure, cold temperatures, and limited communication Each new survey reveals features that reshape understanding of geological processes and marine ecosystems. In summary, mapping the ocean is an ongoing endeavor that blends technology, patience, and global cooperation. From weighted lines to sonar arrays and satellite altimetry, each generation of tools has peeled back another layer of the ocean's hidden landscape. Yet the task is far from complete. As mapping efforts continue, they not only improve navigation and safety, but also deepen understanding of the dynamic planet beneath the waves, revealing a world as complex and varied as any on land. The oceans provide a vast array of natural resources that have supported human societies for thousands of years and continue to shape the modern global economy. From food and raw materials to energy and minerals, marine resources are deeply intertwined with daily life, industrial development, and technological progress. At the same time, the scale and intensity of human use raise complex questions about sustainability, equity, and long-term environmental impact. The most fundamental ocean resource is food. Marine fisheries supply a significant portion of the world's protein intake, especially for coastal and island populations. Fish, shellfish, and other marine organisms have been harvested for millennia using methods that evolved from small-scale subsistence fishing to large industrial operations. Advances in refrigeration, navigation, and vessel design enabled fishing fleets to operate farther offshore and remain at sea longer, dramatically increasing catch volumes. Aquaculture has expanded rapidly in recent decades, producing fish, crustaceans, and seaweed in controlled environments to supplement wild catches and meet growing demand. Beyond food, oceans are a major source of salt, one of the earliest marine resources exploited by humans. Seawater evaporation has been used for centuries to produce salt for food preservation, seasoning, and industrial processes. Salt extraction remains economically important in many coastal regions, linking ancient practices with modern supply chains. In addition to salt, seawater contains a wide range of dissolved minerals, some of which are extracted for industrial use, although most remain economically impractical to harvest at large scales. The seafloor holds significant deposits of oil and natural gas, particularly along continental shelves. Offshore drilling has become a major component of global energy production, supplying fuel for transportation, electricity, and manufacturing. Technological advances have allowed drilling operations to move into deeper waters, extending resource access far beyond the coastline. While these developments have increased energy availability, they also carry risks, as accidents and spills can cause long-lasting damage to marine ecosystems and coastal communities. In recent years, attention has turned toward mineral resources found in the deep ocean. Polymetallic nodules, cobalt-rich crusts, and hydrothermal vent deposits contain valuable metals such as manganese, nickel, cobalt, and rare earth elements used in electronics and renewable energy technologies. These resources are distributed across vast areas of the deep sea floor, particularly in parts of the Pacific Ocean. Deep-sea mining has not yet been widely implemented, but exploration efforts have raised concerns about potential impacts on poorly understood ecosystems that may be highly sensitive to disturbance. Oceans are also an important source of energy beyond fossil fuels. Tidal energy harnesses the predictable rise and fall of sea levels caused by gravitational interactions, while wave energy captures the motion of surface waves generated by wind. Offshore wind farms, though driven by atmospheric processes, rely on marine environments for their placement and operation. These renewable energy sources offer opportunities to reduce carbon emissions, but they also require careful planning to minimize effects on marine life, navigation, and coastal landscapes. pharmaceuticals have been developed from substances originally discovered in sponges, algae, and marine microorganisms. Enzymes from deep-sea bacteria are used in biotechnology because of their ability to function under extreme conditions. As exploration expands, the potential for new discoveries grows, highlighting the ocean as a reservoir of biological innovation. The oceans also support global infrastructure in ways not immediately visible. Undersea cables laid across the seafloor carry the vast majority of international data traffic, enabling global communication and commerce. While not a consumable resource in the traditional sense, the ocean's physical space and stability make this infrastructure possible, turning the seafloor into a critical component of the modern digital economy. Access to ocean resources has always been uneven, shaped by geography, technology, and political power. Coastal nations with advanced fleets and capital have historically benefited most, while small-scale fishers often face competition and declining stocks. International waters further complicate resource governance, requiring cooperation among nations to manage shared resources and prevent conflict. The growing demand for ocean resources has intensified concerns about sustainability. Overexploitation, habitat destruction, and pollution can degrade the very systems that provide these benefits. Many resources regenerate slowly, if at all, and damage to marine ecosystems can have cascading effects that reduce productivity over time. This has led to increasing emphasis on ecosystem-based management, precautionary approaches, and international regulation. In essence, ocean resources are both a foundation of human prosperity and a test of collective responsibility. They offer food, energy, materials, and scientific opportunity on a scale unmatched by any other environment on Earth. How these resources are managed will determine whether the oceans continue to support human societies or become depleted and degraded. Understanding their value, limits, and interconnectedness is crucial for ensuring that ocean wealth remains available for future generations. The oceans form the backbone of global trade, functioning as the primary highways through which goods, resources, and energy move between continents. Long before modern infrastructure existed on land, maritime routes connected distant societies, enabling exchange on a scale unmatched by overland travel. Even in the age of air freight and digital commerce, the vast majority of physical goods traded worldwide still move by sea, underscoring the ocean's central role in the global economy. Maritime trade expanded alongside advances in shipbuilding and navigation. Early trade routes followed coastlines and relied on predictable winds and currents. Over time, sailors learned to cross open oceans, transforming seas into reliable corridors rather than barriers. This shift allowed regional economies to integrate into global networks, accelerating specialization and economic interdependence. Bulk goods such as grain, timber, metals, and textiles could be transported efficiently across thousands of kilometers, reshaping patterns of production and consumption. Today, global trade depends heavily on large commercial vessels designed to move massive quantities of cargo at low cost. Container ships, tankers, and bulk carriers dominate the oceans, transporting everything from consumer electronics and clothing to oil, liquefied natural gas, and raw materials. Standardized shipping containers revolutionized trade by allowing goods to be packed once and transferred seamlessly between ships, trains, and trucks. This efficiency dramatically reduced transportation costs and made global supply chains viable. Ocean trade routes are not evenly distributed, but concentrated along key corridors. Major shipping lanes connect industrial centers, resource-producing regions, and population hubs. Routes across the Atlantic link Europe and North America, while while those spanning the Pacific Ocean connect East Asia with the Americas. Strategic choke points such as narrow straits and canals handle enormous volumes of traffic, making them economically vital and geopolitically sensitive. Disruptions in these areas can ripple through global markets within days. Ports are the critical interfaces between sea and land trade. Modern ports are complex logistical hubs equipped with cranes, storage facilities, rail links, and digital tracking systems. They must handle increasing ship sizes and ever-growing cargo volumes while maintaining efficiency and security. Successful ports can drive regional economic growth by attracting industry, creating jobs, and integrating local economies into global trade networks. Conversely, inadequate port infrastructure can become a bottleneck that limits development. Beyond goods, oceans also carry the infrastructure that enables global commerce itself. Thousands of kilometers of undersea cables crisscross the seafloor, transmitting data that underpins international finance, communication, and coordination. Although invisible to most people, these cables are essential to modern trade, allowing markets, shipping companies, and governments to operate in real time. The ocean thus supports not only physical trade, but also the digital systems that manage it. Maritime trade is closely tied to energy flows. Oil and gas tankers move fuel from production regions to consumers worldwide, while coal and refined products follow similar routes. Energy security for many nations depends on uninterrupted access to these sea-based supply lines. This dependence has historically influenced naval strategy and continues to shape international relations as nations seek to protect shipping lanes critical to their economies. The scale of ocean trade brings environmental and social challenges. Large vessels emit greenhouse gases and air pollutants, contributing to climate change and coastal air quality issues. Accidental spills, ballast water discharge, and noise pollution can harm marine ecosystems. Additionally, the global shipping workforce operates under demanding conditions, raising concerns about labor standards and safety. Addressing these issues requires international cooperation, as ships routinely operate across multiple jurisdictions. Climate change is beginning to affect ocean trade itself. Rising sea levels threaten port infrastructure, while changing storm patterns increase risks to shipping. Melting polar ice is opening new routes in high-latitude regions, potentially shortening travel distances, but also introducing environmental and geopolitical uncertainties. At the same time, pressure is growing to decarbonize shipping through cleaner fuels, improved efficiency, and new vessel designs. In essence, the oceans are the circulatory system of the global economy. They enable the movement of goods, energy, and information on a scale that no other transport system can match. Modern globalization, with its tightly linked supply chains and worldwide markets, would not exist without maritime trade. Understanding the role of oceans in global commerce reveals how deeply economic prosperity depends on the stability, accessibility, and health of the seas. Marine ecosystems are structured around complex food webs that govern how energy and matter move through the ocean. Unlike simple food chains, which suggest a linear sequence of who eats who, marine food webs consist of dense networks of interactions among organisms of different sizes, life stages, and ecological roles. These webs determine population stability, biodiversity, and the overall productivity of the oceans, making them central to understanding how marine environments function. At the base of nearly all marine food webs are primary producers, chiefly phytoplankton. These microscopic organisms use sunlight, carbon dioxide, and nutrients to perform photosynthesis, converting inorganic matter into organic biomass. Although individually tiny, phytoplankton collectively form one of the largest and most important biological communities on Earth. They support almost all higher marine life and drive the initial capture of energy that fuels ocean ecosystems. Primary producers are consumed by primary consumers, such as zooplankton, small crustaceans, and some filter-feeding animals. Zooplankton include a wide range of organisms, from tiny single-celled species to larger animals like krill. These organisms graze on phytoplankton and convert plant energy into animal biomass, forming a crucial link between microscopic producers and larger predators. In many regions, fluctuations in zooplankton populations directly influence fish stocks and higher trophic levels. Above them are secondary and tertiary consumers, including fish, cephalopods, seabirds, and marine mammals. Predatory fish feed on smaller fish and invertebrates, while apex predators such as sharks, large tuna, and whales occupy the top of the food web. These top predators often have few natural enemies and play a disproportionate role in regulating ecosystem balance. By controlling prey populations, they help prevent overgrazing of lower trophic levels and maintain species diversity. Marine food webs differ significantly from those on land because of the ocean's three-dimensional nature. Organisms interact not only horizontally, but also vertically, moving between surface waters and deeper zones. Many species undertake daily vertical migrations, feeding near the surface at night and retreating to depth during the day to avoid predators. This vertical movement transfers energy and nutrients through the water column and links surface productivity with deep-sea ecosystems. Another defining feature of marine food webs is the importance of detritus, dead organic matter such as fecal pellets, discarded shells, and decomposing organisms. Much of the energy captured at the surface does not pass directly to large predators, but instead sinks as organic debris. Bacteria and detritivores break this material down, recycling nutrients back into the system. In deep-sea environments, where sunlight does not penetrate, detritus falling from above is often the primary source of energy. Ecosystem structure varies widely across different marine environments. Coastal food webs tend to be highly productive and complex due to abundant nutrients from land runoff and upwelling. Coral reef ecosystems support intricate webs involving thousands of species tightly linked through mutualism, predation, and competition. Open ocean food webs are generally more diffuse, spread over vast areas, while polar food webs are often simpler but highly seasonal, driven by short bursts of intense productivity. Large-scale ocean regions, such as the Pacific Ocean, host multiple interconnected food webs, rather than a single uniform system. Currents transport organisms, larvae, and nutrients across enormous distances, linking ecosystems that may be thousands of kilometers apart. Changes in one region can therefore propagate through food webs elsewhere, illustrating how interconnected marine life truly is. Human activity has increasingly altered marine food webs. Overfishing can remove key predators or prey species, triggering cascading effects known as trophic cascades. For example, the loss of top predators may allow mid-level consumers to increase unchecked, reducing populations of smaller species and altering habitat structure. Pollution and climate change further disrupt food webs by affecting productivity, species distribution, and timing of biological events such as spawning and migration. Climate-driven changes in ocean temperature and chemistry are reshaping food webs on a global scale. Warming waters can shift plankton communities towards smaller species, reducing the efficiency of energy transfer to higher trophic levels. Ocean acidification can impair shelf-forming organisms, altering the availability of prey for many species. These changes may reduce overall ecosystem productivity and resilience, particularly in already stressed regions. Despite their complexity, marine food webs are remarkably efficient at recycling energy and nutrients. They have evolved over hundreds of millions of years to function under conditions ranging from sunlit surface waters to the darkness of the deep sea. However, their stability depends on maintaining the balance among trophic levels and the environmental conditions that support them. The oceans are powerful natural systems capable of generating hazards that can profoundly affect human societies and coastal environments. While the sea sustains life and facilitates global exchange, it also produces some of the most destructive forces on Earth. Storms, extreme waves, tsunamis, and long-term coastal erosion arise from interactions between ocean dynamics, atmospheric processes, and geological activity. Understanding these hazards is essential for reducing risk and improving resilience in a world where coastal populations continue to grow. One of the most significant ocean-related hazards is severe storms. Tropical cyclones, known by different names such as hurricanes or typhoons depending on region, form over warm ocean waters where heat and moisture fuel their development. As these systems intensify, they generate powerful winds, heavy rainfall, and storm surges that can inundate coastal areas. Storm surge, the abnormal rise of sea level driven by wind and low pressure, is often the deadliest component, flooding low-lying regions far inland. Warmer ocean temperatures can increase storm intensity, making the ocean's thermal state a critical factor in storm risk. Beyond storms, the ocean can produce extreme surface waves that pose dangers even in otherwise calm weather. Rogue waves, sometimes called freak waves, are unusually large and sudden waves that can rise dramatically above surrounding seas. Once considered myths, they are now well documented through satellite data and ship observations. Rogue waves can damage vessels and offshore structures, appearing with little warning and releasing immense energy in a concentrated area. Their formation is linked to the complex interaction of currents, winds, and wave interference, particularly in regions with strong opposing currents. Tsunamis represent a different category of ocean hazard, driven not by weather but by geological events. Underwater earthquakes, volcanic eruptions, and landslides can displace massive volumes of water, generating long wavelength waves that travel across entire ocean basins at high speed. In the open ocean, tsunamis may be barely noticeable, but as they approach shallow coastal waters, they slow down, increase in height, and release devastating force. Events originating in regions such as the Pacific Ocean can affect coastlines thousands of kilometers away, highlighting the global reach of these hazards. Coastal erosion is a slower but persistent ocean hazard that reshapes shorelines over time. Waves, tides, and currents continually wear away coastal land, transporting sediment and altering beaches, cliffs, and deltas. While erosion is a natural process, it can be accelerated by storms, sea level rise, and human activities such as coastal construction and sand mining. In many regions, erosion threatens homes, infrastructure, and ecosystems, forcing communities to choose between costly protective measures, relocation, or accepting gradual land loss. Another hazard arises from the interaction between ocean conditions and human infrastructure. Strong currents and waves can undermine offshore platforms, damage undersea cables, and complicate navigation. In polar regions, drifting sea ice and icebergs pose risks to ships and coastal installations. These hazards require constant monitoring and adaptive engineering to ensure safety and reliability in harsh marine environments. The ocean also amplifies hazards through compound effects. A storm coinciding with high tide can dramatically increase flooding risk, while heavy rainfall combined with storm surge can overwhelm drainage systems. tsunami impacts may be worsened by coastal subsidence or the loss of natural barriers such as mangroves and reefs. These interacting factors make hazard prediction and management complex, requiring integrated approaches that consider both oceanic and terrestrial processes. Advances in science and technology have improved the ability to monitor and forecast ocean hazards. Satellite observations track storm development and wave heights, while buoy networks measure sea level changes and seismic sensors detect underwater earthquakes. Early warning systems for tsunamis and storms have saved countless lives by providing time to evacuate or prepare. However, warnings are only effective when coupled with public awareness, clear communication, and well-planned response strategies. Climate change is altering the landscape of ocean hazards. Rising sea levels increase baseline flooding risk, making storm surges more damaging, even if storm frequency remains constant. Changes in ocean temperature and circulation may influence storm behavior and wave patterns. As a result, hazards that were once considered rare may become more frequent or severe in certain regions, challenging existing infrastructure and preparedness plans. In essence, natural ocean hazards reflect the immense energy and dynamism of the marine environment. They are an inherent part of Earth's system, capable of shaping coastlines and influencing human history. While these hazards cannot be eliminated, their impacts can be reduced through scientific understanding, careful planning, and respect for the powerful forces at work in the oceans. The future of Earth's oceans will be shaped by the interplay between natural processes, human activity, and global efforts to understand and protect marine systems. Oceans remain central to climate regulation, food security, biodiversity, and economic activity, yet they face unprecedented pressures from pollution, overfishing, habitat loss, and the accelerating effects of climate change. How humanity responds to these challenges will determine whether the oceans continue to sustain life and support societies, or experience irreversible degradation. One of the most immediate and visible future changes is sea level rise. As global temperatures increase, glaciers and polar ice sheets melt and warmer water expands, raising ocean levels. This trend threatens low-lying coastlines, island nations, estuaries, and deltas that are home to hundreds of millions of people. Rising seas exacerbate flooding, saltwater intrusion, and coastal erosion, forcing societies to reconsider urban planning, infrastructure, and settlement patterns. Adaptive strategies such as seawalls, managed retreats, and wetland restoration will be critical for reducing vulnerability while balancing ecological impacts. Climate-driven changes in ocean temperature and chemistry will also shape the future of marine ecosystems. Warming waters may shift species distributions poleward, alter migration patterns, and change the timing of reproduction and feeding cycles. Ocean acidification, caused by continued carbon dioxide absorption, threatens shell-forming organisms and coral reefs, potentially restructuring entire ecosystems. Combined with deoxygenation in certain regions, these changes may reduce biodiversity, productivity, and the resilience of marine systems, with cascading effects on fisheries and food security. Human use of ocean resources will continue to evolve. Fishing practices may become more regulated and sustainable as international agreements, technology, and consumer awareness advance. Aquaculture may expand to supplement wild fisheries, while renewable energy from offshore wind, tidal, and wave systems could increase, providing clean energy while altering marine environments in subtle ways. Deep-sea mining and resource extraction may become more common, raising questions about ecological impact, governance, and the limits of sustainable exploitation. The challenge will be to balance economic benefits with conservation and long-term ecosystem health. Marine conservation will play a pivotal role in shaping the future. The expansion of marine protected areas, restoration of habitats such as coral reefs, mangroves, and seagrasses, and ecosystem-based management approaches can maintain biodiversity, enhance carbon sequestration, and protect ecosystem services. Global coordination will be essential, particularly in international waters where governance is more complex. Conservation will need to adapt to dynamic ocean conditions, incorporating climate projections and monitoring to ensure protection remains effective under shifting environmental baselines. Technological innovation will continue to transform our understanding and management of oceans. Autonomous underwater vehicles, advanced sensors, satellite monitoring, and machine learning provide unprecedented insights into physical, chemical, and biological processes. These tools allow scientists to detect changes, predict hazards, and develop solutions for sustainable management. Biotechnology and marine-derived materials may offer novel solutions for medicine, industry, and renewable energy, further connecting human progress with the ocean's unexplored potential. Global cooperation and governance will be essential to the future of oceans. International agreements such as the United Nations Convention on the Law of the Sea and emerging frameworks for biodiversity beyond national jurisdiction provide mechanisms for equitable management of shared resources. Collaboration in research, monitoring, and conservation ensures that knowledge and responsibility are distributed fairly, preventing conflicts and promoting sustainable use. Public engagement and education will also be vital, as individual choices regarding consumption, pollution, and support for conservation influence ocean health. The oceans will also continue to serve as indicators of planetary change. Shifts in currents, temperature, and chemical composition offer early warnings of broader climate impacts, while the health of marine species reflects the cumulative effects of human activity. In this sense, the future of the oceans is intertwined with the broader trajectory of Earth's environmental systems and humanity's capacity to act responsibly. Finally, human stewardship will determine whether the oceans remain resilient and productive. Sustainable practices, protection of habitats, reduction of pollution, and careful management of resources can preserve the oceans as a source of food, climate regulation, cultural value, and inspiration. Failure to act could lead to degraded ecosystems, collapsed fisheries, loss of biodiversity, and diminished capacity to buffer climate change, with far-reaching consequences for societies worldwide. In essence, the future of Earth's oceans is both a challenge and an opportunity. They hold the potential to continue sustaining life, enabling economies and inspiring exploration, but only if humans act with foresight, cooperation, and care. Balancing use and protection, integrating technology and knowledge, and adapting to changing conditions will be essential. The ocean's long-term survival depends on our willingness to manage them wisely, ensuring that these vast and vital systems remain healthy, productive, and resilient for generations to come.